so let's review real quickly the properties that we looked over. We already had said that matrix multiplication was not commutative. We said the associative property does apply with matrix multiplication. And you can see here, when you have three matrices multiplied together, you can actually just look at the dimensions and tell whether or not it's going to be possible for all three of them to be multiplied. Okay, because for example, in this case, A is a 5 by 3 matrix, B is a 3 by 7, and C is a 7 by 2. Alright, so in order to be able to multiply A and B, the number of columns in A has to equal the number of rows in B, and it does. And then in order to multiply B by C, the number of columns in B has to equal the number of rows in C. Alright, so seeing this shows us that yes, I can multiply this. When I do AB, I'll get a 5 by 7 matrix, and then that is possible to multiply by a 7 by 2 matrix. Okay? Or if I did BC first, okay, BC would give me a 3 by 2 matrix, and I can multiply a 5 by 3 matrix by a 3 by 2 matrix. Okay? In both cases, though, notice we'll get a 5 by 2 matrix at the end. Okay? Then we have the distributive property, and it's really important that you remember that matrix multiplication is not commutative when you're doing the distributive property. Because when we're dealing with real numbers, most of the time, if you had seen something like this, you would have automatically brought that number out to the front. Okay? But here, when you have a set of parentheses times some matrix, you do distribute, but you have to distribute, in this case C, after the A and after the B. So it'd be AC plus BC. Okay? And you can't just rewrite it as C times A plus B. Alright? Because that'll be different. Alright? We often did rewrite it with real numbers. You can't here with matrices. And then we had the associative property when we had scalar multiplication. The basic thing is here, if you've got a scalar and you've got a product of matrices, you can put that scalar in anytime you want. You can multiply the first one by the scalar, you can multiply the second one by the scalar, or you can do the matrix multiplication first and then multiply by the scalar. Okay? It doesn't matter when you do it, you just at some point multiply by the scalar. Okay? So there may be benefits, depending on the problem, to waiting until the end or to doing it first or whatever. Okay? Now, the application I want to look at here is, we've got some data here. It says 2 softball teams submit equipment lists to their sponsors, as shown in the table. Each bat costs $80, each ball costs $6, and each glove costs $60. Okay? So you'll notice here the women's team needs 12 bats, 45 balls, and 15 gloves. The men's team needs 15 bats, 38 balls, and 17 gloves. So what we end up doing here, if we want to find the total cost of equipment for each team, what we're going to do is set up 2 matrices. We're going to set up a cost matrix, okay? In our cost matrix, we have 3 items, and each one costs a different price. So we could make it 80, 6, and 60. Okay, that'll be our cost matrix. And what are the dimensions of this matrix?
3 by
1 by 3. 1 by 3. And one thing that's really helpful when you're doing this in a word problem is not only to write down what the dimensions are, but also to write down what the dimensions represent. Okay? The row represents the price, right? And the columns are the different equipment. Okay? Just to be consistent with the terminology over here. It's the price by the type of equipment. Alright? Now, we also have a matrix we could make given this data. Okay? We could call it the equipment matrix. Okay? Alright? And let's think about it, because you guys know to find the value of a number of things, you have to do the price times how many you have. Okay? So we're going to multiply the cost by how many items we have. So think about it. If I'm going to multiply cost by equipment, what has to be true about the dimensions of our equipment matrix? Okay, it's going to be, it has to have 3 rows. Okay? And if there are 3 rows, that means the equipment is the row. And the 2 is going to be our team. Okay, the equipment by team matrix. Alright? So you see how we're relating the dimensions, or relating the rows and columns to what they represent. Now that's important because, you know, we write down this matrix here, and it's actually going to look just like the table, 12, 15, 45, 38, 15, 17. And now when we multiply them, okay, what kind of matrix are we going to have?
1 by 2.
It's going to be a 1 by 2 matrix. And notice what it's going to give us. The 1 was the cost or price. Actually, I'm going to change this to cost because just to be consistent. Okay? So this is going to be cost by team. Okay? The cost by team matrix. So when we get this 1 by 2 matrix, the 2 numbers in it are going to represent how much money it's going to cost to get all the women's team's equipment and how much money it's going to cost to get all of the men's equipment. Alright, so we can then figure that out. We're going to have to do 80 times 12 plus 6 times 45 plus 60 times 15. Okay? What'd you get? 1,915?
No, 15.
50?
Yeah.
Okay, can someone confirm that, just to double check?
Yes. 12 times
12 times 80, 6 times 45, 60 times 15.
what? Oh, 15 times 60.
15 times 60.
2, 1, 30.
2, 1.
Yeah, 2, 130.
2, 130.
Yeah.
No,
Okay, 80 times 12, 6 times 45, 60 times 15. This is 2130. So that's how much all of the women's equipment is going to cost. Alright, so if we figure out the other element, that's going to tell us how much the men's equipment is going to cost. So here we're doing 80 times 15, 6 times 38, 60 times 17.
2, 4, 4, 8.
2,
2, 4, 4, 8? Okay. So, now that they have a breakdown per team, okay, the sponsor might say, okay, we need to cut down on a little bit of this, so, you know, or maybe they're budgeting for next year, and this is what happened this year. Okay, so they can make adjustments once they have both numbers. But the idea is this: we're not having to go through all of the data and do the same kind of process twice. By using a matrix, we're just doing one multiplication problem, and all of the work gets done as we multiply the matrices together. Okay. So, let's just skip down here and take a look at a couple of problems here. We're not going to actually do the multiplication, but I want to interpret some results here. All right, so 80. A manufacturer produces 3 models of portable CD players, which are shipped to 2 warehouses. Okay. So looking at this matrix A, what do the rows represent?
Amount of CDs.
Okay, the models of CDs, of CD players. Okay, there are 3 models, and the 2 columns represent what? Okay.
I and J.
Do you
the
know the
warehouse.
Yeah, the warehouses. Yeah. Okay. Okay, so we have the models by the warehouses. Okay, and then it says the price per unit. Okay, so obviously we're talking about money, but what do the columns in matrix B represent?
Quantity.
The what?
The unities. Quantity.
No, the
Oh, no, on A, my bad. The price per unit.
models.
Per models. Okay, this model costs $39.50. This is $44.50. This is $56.50. Okay, so we have a price by model matrix. Okay, so they're asking, you know, what would BA represent? Okay,
Price per
The
word.
three.
The-
BA.
No,
BA.
the price for each warehouse, like both the warehouses.
No. Total amount that
Money.
they have per warehouse.
Okay, yeah, you could think of it as price. You're going to end up getting your prices by warehouse,
It's taking
but what is that price? The price,
Unity. Per unit.
okay,
Unity?
He's taking the inventory.
Yeah.
alright, we're going to get, think about what kind of a matrix we're going to get. This is a 1 by 2, or a 1 by 3, right? And this is a 3 by 2. So when we multiply those, we're going to get
We can't.
a 1 by 2. Well, we're doing BA, not AB.
Oh.
Oh.
We can't do AB, you're right. But BA, alright, here's A, here's B. BA is going to be a 1 by 2 matrix. It's going to be a price by warehouse. And when we're talking about price, that's going to be the total value of the inventory at each warehouse. Okay? The value of everything combined at each warehouse. Okay? So, being able to interpret your answer is important, okay? So once we do B times A, then we'll know what the value of our inventory at the first warehouse is and what the value of the total inventory at the second warehouse is. Okay? So if one burns down, we know what it was all worth, okay?
And collect that insurance money.
Yeah.
Alright, here's another case where we have a company selling 5 different models of computer and we're selling it through 3 different retailers.
Oh.
Okay, so 3 different stores are selling our 5 different computers. And the inventories are given by S, okay? So then it says the wholesale and retail price of each model is given in T, alright? So let's think about this. If I do S times T, first of all, what are the dimensions of that matrix going to be?
S times 3 by, or no,
2 by
5.
A 3 by
2.
2 by
2.
It's gonna be wholesale versus retail at each outlet.
Okay, if I'm doing S times T, it's going to be an outlet by
Price.
price. Okay,
Very expensive computers.
yeah.
$3,200 for a computer.
Actually, you could pay $3,200 for a computer nowadays.
Yeah.
A real top end one,
That is ridiculous.
but
I'd get like the 840
you
one.
get one of those like Alienware gaming
Mac
computers.
Yeah.
or something.
Pro is more like 5K.
Oh, the Macs are ridiculous.
Why-
Anyways, we have outlet by price. So what does that mean? That's going to give us the value of the inventory at each store. Okay? This is going to give us the value 2 ways. Okay? And that's going to give us the wholesale and the retail. You guys know what wholesale and retail are?
Yeah.
Wholesale is what, like, if one of these was Best
What
Buy.
the stores
Best
buy
Buy
it for
buys it
every
from the manufacturer at a certain price. That's the wholesale price because they're buying a whole bunch of them. So the manufacturer gives them a discount. Then they turn around and sell it for more, obviously, because that's how they make a profit. That's the retail price. Okay? It'd be just like if, if you went to the store and bought, a case of pop, that would be your wholesale price. And then if you turned around and sold the pop or soda, or for if you sold it for, if you sold them for, 75 cents a piece, that would be your retail price. Okay? So here you're getting the value wholesale and retail at each location. Alright, at each outlet. Okay. Okay. Alright, so I think you guys are getting the idea of those, but again, interpreting your answer is really important to be able to do. Okay? Alright, any questions? Comments? Anything? Yes?
Do they ever use, so these are all like 2-dimensional matrices. Are there ever 3-dimensional matrices where you have like row by column by depth or something?
By depth, in computer programming, I think they have that. There's a data type that you can do that. Basically, you're making a cube to hold your data
to hold
with.
the data, it would make sense.
I think they can do that in computer programming, and it'd be hard to
You
draw
can't write
here,
it on
but
paper, yeah.
it'd be hard to put on paper. But in
You can have that digitally.
yeah, digitally you could do it. But yeah, now all the operations would be different.
Yeah, because multiplication.
How would you
think of a new
multiply those
process.
together? it'd be more for data storage,
Yeah.
you know, than it would be for necessarily for this. Basically, what you would have is you would have a matrix where each element is a matrix.
Yeah.
And that you can do in computer programming. You can, like when I took C++, you could have a matrix, but anything could go in that matrix as the different elements. So I could have a matrix, and within each matrix, I have a whole matrix of stuff. And if you think about it, that's kind of how a database is built.
Yeah.
A database has all these categories, and then within those categories are subcategories and subcategories. Really, it is kind of a matrix structure there, if you think about it. So, good question. Alright, so, what we want to look at in the remainder of our time today is we're going to start talking about the inverse matrix. Okay? We talked about multiplication. And we're dealing with, we want to look now at inverses of a matrix. And really, we need to think back to our beginning Algebra 1 days to kind of get the sense of where we're going with this. Okay? When we were dealing with real numbers, the inverse in multiplication was the reciprocal. Okay? So if we multiplied something by its reciprocal, we got the identity. So 5 times 1/2 equaled 1. And we used that in defining inverse operations. For example, if I have 5x equals 10, technically what you're doing in doing inverse operations is you are multiplying by the inverse, okay? Or you are doing an inverse operation. We recognize that multiplying by the reciprocal is the same thing as dividing, okay? And of course we would have to do that on both sides. But the whole idea is this. When we did this, we got the identity, okay? We got the identity 1, right? Now with matrices, the concept is the same, but it's not quite as simple, alright? But understanding the concept is important here. So let's first of all define what the identity matrix is, okay? The identity matrix is, it says an n by n matrix. It's a square matrix, we call it, because the rows and the columns, you have the same number of rows as you have columns. Alright? So you can't have a 4 by 3 identity matrix. It would have to be a 4 by 4 or a 3 by 3 or a 2 by 2. But here's the key. It has 1s on its main diagonal from the top left corner to the bottom right corner, and it has 0s everywhere else. Okay? It looks a lot like the row reduced echelon form. In fact, if you remember, you had this. And then you had your column of answers. Well, this by itself is the identity for 3 by 3 matrices. Okay? Now, notice it says the order is understood to be n. You can denote I sub n. We use a capital I to represent our identity matrix. Okay? And I could call this I sub 3 because this is a 3 by 3 matrix. Okay? If I wanted I sub 2, I would just have 1, 0, 0, 1. Okay? That would be my my identity, for 2 by 2 matrices.
Oh, that's an I on that side. I N.
Yes, that's an I right here. I sub n. Okay? Alright? Now, the reason why I start looking at the identity when we're talking about the inverse is because remember, when we use the inverse, we should end up with the identity. Okay? Now, some notation here. If you see a to the negative 1 power, okay, that's not an exponent, that's an inverse. That's notation for an inverse. You've seen this with your sine, cosine, and tangent functions. Okay? It's an inverse sine negative 1, cosine negative 1, tangent negative 1. Those were inverse functions. Here we have an inverse matrix. And notice what happens here, okay? Any matrix times its inverse will give us the identity matrix,
Why doesn't it give you 1?
okay?
The identity
Well,
matrix is
1 is the identity for multiplication with real numbers. 1 is not the identity for matrices, okay? Our identity is a matrix, okay? Likewise, if I turn it around and I say A inverse times A, I'm going to get the identity again. So here, remember how I said matrix multiplication is not commutative? The only exception is when you have inverses or if you're dealing with the identity in some way, okay? So let's look at, in this case, let's show that B is the inverse of A. So how would we do that? Multiply them. And what should I get?
an identity matrix that's 2 by 2.
Okay, the question is, do I get this when I do A times B and when I do B times A?
But do you need to do both?
It has to work both ways.
So 1 times.
Okay? It has to work both ways. Okay, so let's try it. Alright? If I do A times B, I have negative 1, 2, negative 1, 1 times 1, negative 2, 1, negative 1. So, just working this out, I have negative 1 times 1 is negative 1, plus 2 times 1 is 2. Okay? I have negative 1 times negative 2, which is positive 2, plus 2 times negative 1 is negative 2. And then for my second row, I have negative 1 times 1 is negative 1, 1 times 1 is 1, and then I have negative 1 times negative 2 is 2.
This is A times, yeah, that's A times B, right?
Yes, A times B. And then 1 times negative 1 is a negative 1. So look at what we get. Negative 1 plus 2 is 1. 2 minus 2 is 0.
1, 0, 1, 0.
Negative 1 plus 1 is 0. 2 minus 1 is 1. So, I showed that AB at least does equal the identity. Okay?
But when you find that A minus, so it's not A.
Well, no. We're showing that B is the inverse.
Oh.
Okay? We're trying to show that B is the inverse. So if that's the case, then when I multiply B by A, I should get the identity.
Oh, yeah, one.
Because if it's the inverse, then A times its inverse will be the identity. Okay? So, now if we do BA, okay, same idea, except we switch it around. 1, negative 2, 1, negative 1,
So can I use that?
negative 1, 2, negative 1, 1, okay? So, negative 1 plus 2 2 minus 2. Then we have -1 plus 1. And then we have 2 minus 1. Okay? Once again, we get 1, 0, 0, 1. So, therefore, B is the inverse of A. Okay?
Would you just be able to tell by, like, if you look at the numbers, how they're just the opposite? Or
No. In this case, yeah, multiplying by -1 did actually give us the inverse, or would actually give us the inverse. That's not always going to be the case. That's a good observation, but that's just coincidence for this example. Okay? Now, to finish up here, I want to just look at 2 by 2 matrices only. Okay? Only 2 by 2 matrices. And there's actually 3 different ways we could find the inverse of a 2 by 2 matrix. Okay? 2 ways you can use even if you have 3 by 3 matrices, 4 by 4 matrices, any matrix, any size matrix. These first 2 ways we're going to look at, that's the case. The last way is a formula, but that only applies to 2 by 2s. Okay, so the formula is actually an easier way of getting the inverse of a 2 by 2 matrix. These first 2 ways, however, will work no matter how many, no matter what the dimensions are. Now, one thing I'm going to do is, this is really annoying to have x11, x12, x21, and x22. So what I'm going to do instead is make those A, B, C, and D. Okay? That'll be a whole lot easier to keep track of. Alright? And easier to write. The first way of finding the inverse of this A here, 1, 4, -1, -3, would be to say, okay, well, if this is the case, or if this matrix is the inverse, then when I multiply A by this matrix, I should get 1, 0, 0, 1, right? So, let's make that happen, okay? Let's figure out what A, B, and C, and D would have to be in order to get that to work, okay? So let's go through the matrix multiplication here. A times X, alright? So, watch, first row, first column, I have 1 times A plus 4 times C, right? So 4C. Is everyone with me there?
yes.
Okay. A, 1 times A plus 4 times C. First row, first column. Now I want to do first row, second column. So 1 times B plus 4 times D. Okay? Now I'm doing second row, first column. -A minus 3C. Okay? And then second row, second column is going to be a -B minus 3D. Okay? Now, that is supposed to equal 1, 0, 0, 1. Right? So what could I do?
So, this
Just
one.
set up a system of equations. A plus 4c
Use a matrix to find the matrix.
equals 1.
Use the matrix to find.
B plus 4d has to equal 0. Okay, negative A minus 3c has to equal 0. And negative B minus 3d has to equal 1. Okay? So now I have a system of 4 equations with 4 unknowns, okay, that I can solve. Alright? And the nice thing is it's actually set up pretty nicely for us. Because look, if I use elimination with these two, okay, if I add those together, what do I get?
C.
Yeah, A plus negative A is 0.
C equals 1.
4c minus 3c is just 1c, and 1 plus 0 is 1. So I know c is 1.
Wait, how do you know that it equals, like, A plus 4C, like, does that mean that it's equal to negative B minus 3D?
No,
Both equal to 1. Like,
no. Well, I mean, technically, yeah, because they're both equal to 1, actually. But we're coming up with our equations by saying, all right, this has to be the identity matrix, so that top left
Oh, I see.
element has to equal 1. Okay? So we add these together, we get C equal to 1, which means A has to be what?
C is 1, A has negative. Wait,
Negative 3?
Negative 3. Okay? So we have 1 and negative 3. Okay? And then we could do the same thing. We can do the same thing with B and D. Okay? Again, this sets up nicely. Even if it didn't set up nicely, we could solve the system of equations. But what do we get on this one?
D
or,
equals 1.
yeah.
D equals 1. And that means B would have to be
Negative
negative
or
4. Okay? So, A inverse then, A inverse is the matrix negative 3, negative 4, 1, 1. Okay?
Can you just switch the numbers around? Oh wait, it's a negative 1, not a 1. I see.
Yeah.
This is where we get the A plus 4C, B plus 4D other.
We got those again because when I multiplied the matrices together, this is what I got.
Why you multiply like this, Bill?
Well, I multiplied like that because remember, if I'm trying to find the inverse, listen, if I'm trying to find the inverse, I'm trying to find A inverse, I know that A times A inverse has to equal my identity, right? That's what makes it the inverse. So using that property, I set up this equation, okay? A times some matrix has to be the identity, okay? So what would that matrix have to be? So that's why I put in the ABCD, and we could then get a system of equations, okay? Now, it is possible for a matrix not to have an inverse. Alright, we'll look at how that comes about on Monday when we look at our other two kinds, our other two ways of finding the inverse, okay? But this is one way, okay? Yes.
When will our test be?
Not next week,
Okay, great.
no. I'll get a specific date as we go
Are we
forward.
having a quiz next week? Probably, right?
Yeah,
Okay.
we'll have
Oh,
some-
great.
When?
alright.